So I'm just gonna sign in as you would sign in, putting in our names there. And then this video, um, let's see here. Um, I'm gonna mute it and then try to make it go, it's already muted. And I'm gonna try to just make it go fast, and we'll kind of discuss things as it goes. So this whole thing is really about batteries. Um, they were used to be called like cells or galvanic cells. Weird stuff on like how they first came across the idea that you could have a battery when they were doing dissections with frogs to try to figure some stuff out. You see they have these two different metals. They had, um, not quite far enough back, like holding the frog with one thing and then using a knife to cut in the other. The frog was already like asleep one way or another. So it wasn't the frog moving it, it was these two different pieces of metal. The metals were different metals. One kind of metal here, maybe we'll say copper. Another metal here, we'll say aluminum. I don't know if those were the metals. We'll just say two different metals, right? Um, and when they made contact with the two different types of metals, the frog would twitch. And they tried a bunch of different things to figure out what was going on, and they realized, hey, just two different kinds of metals, we get something happening. And from that, they came up with, hey, there's something flowing, there's this energy given to the things that are moving. And they were able to come up with and make batteries, essentially. The 1800, they call it the voltaic pile, but it's just a variety of different things layered upon themselves. Oftentimes something like an acid, like a vinegar, maybe some salt water, and then some a different metal or two in there. Aluminum works, maybe some carbon pellets or something like that. And you can end up making a battery that, if they just connected the two ends of the battery to the frog, that would make the frog muscle twitch. Um, so when we start talking about batteries, then batteries are the things that motivate charges to move. They are not the source of charges, they motivate charges to move. We can kind of think about it as, well, the anode is like the side where there's a bunch of chemicals lined up, and where let me rephrase that. Within here, there are some chemicals that would want to have, if it was just a plain old reaction, they would say, hey, we want charges to go from here to here for this chemical reaction to happen. And the way a battery is lined up, the only way the charges can go, they can't go just through there. The way the thing is built, it won't let the charges go through there. So the battery motivates all of the charges that are present in the wire and in the filament. The battery motivates all of those charges to go to move. So like this side, if this side we can think of as having a big negative charge, if this has a big negative charge, any negatives that are in the wire here would get pushed away from that. So any electron that's sitting in this wire, because the atom, it's a wire made of atoms, atoms have electrons, this side of the battery motivates that charge, pushes that charge away from there and goes through this stuff. This is the positive side, and it pulls the negatives towards it. The anode and cathode, we're not going to be huge on terms. Uh, we want to know more about how things work. Names for things often do help. If we want to think about the cathode as being the positive side and the anode as being the negative side, that really works. For me, I always had to do I couldn't remember which one was which. It just always buggered me up. So I tried to focus on the N for anode, thinking anode negative. It's a negative side. So that's how I did it. You don't have to do it that way. You can do whatever you want. But with that battery, what the battery does, it pushes all of the charges that are along inside here. And for that reason, they would say that the battery had, back in the day, they would say that there was an electromotive force, EMF, electromotive force, that made all the charges go through. Over time, what we started to do, instead of saying electromotive force, we started to talk about electric potential, and electric potential is measured in volts. So here, this guy is making a battery out of, there's the acid and a lemon, and two different types of metals that both want electrons different amounts. And if they want electrons different amounts, well, that difference is going to push charges from one side to the other. There's your electromotive force, or your electric potential, your voltage. So that's what we're talking about for those things. And it used to be really common for kids, for there to be different kits where you could do things like run a clock off of a lemon or a potato or things like that. And all those things did was they just had two different little strips of metal, a copper side and some side that wasn't copper, a different side, a different metal, and how much they like or want electrons is a little bit different. And so current would flow. Batteries, electric potential, potential difference. So the chemicals, now we're back here. And I'm gonna have to go kind of quick because I'm gonna have another class coming in here in a couple of minutes. So we'll try to do some of this stuff quickly here. Chemicals inside a battery push negative charges away from one side. And this motivates all the charges in the wires connected to the battery to move. If we think of imaginary positive charges, like conventional current, if we think of imaginary positive charges moving through the wire, the positive charges would get pushed away from the positive side of the battery, right? Opposites attract, like charges repel. Positive charges would get pushed away from the positive side of the battery, the cathode. This is similar in asking about the negative charges. If instead of thinking about imaginary positive charges, if we think about electrons, not imaginary, if we think about electrons, the negative charges, which side would they get pushed away from? Well, negative electrons would get pushed away from the negative side of the battery. Next. So these are some things that we have discussed. The first part, we have discussed current. It's how many charges pass by per second. It's kind of like charge per second or coulombs per second. And a coulomb per second or a charge per second, we talk about measuring amps or amperes, capital A. These things are things that we hopefully already have, we've discussed already, and you might already have written down on your own. Some of that stuff can go in here when we start talking about our notes for this stuff. Electric potential, new today. Prior to today, we talked about current, we talked about flow, we talked about amps, coulombs per second, charges per second. Today, new term, new thing. Today, electric potential. Electric potential, that's energy per charge. It's sometimes helpful to think about the energy possessed by a charge when it's at a location. So an electron here has a certain electric potential or voltage. An electron here has a different electric potential or voltage, or electromotive force. We go back to the frog. Yeah. We can talk about electric potential as being the energy each charge has at its location. It's measured in volts. Electric potential is considered by some to be the more technical and accurate, correct term. Many folks use voltage as a synonym for that. Some people find that to be an abomination. Yeah. The symbol for electric potential is V. Now, potential difference is if we have one charge here and then it goes here, well, at these two different locations, that charge might have different electric potentials. The difference is, well, the potential difference or the electrical potential difference, the change in voltage or potential difference. And if there's a difference in voltage or a difference in electric potential between those two locations, well, then a charge is going to move, just like things roll downhill. Well, because there's going to a lower gravitational potential energy. Well, if there's a different electrical potential at these two spots, a charge is going to change position to go to the spot with a better electric potential for it. All right, and the symbol for that is this delta V, or difference, change in potential. Voltmeter. So the voltmeter is a thing that compares the electric potential at one spot to another spot. Voltmeters have two wires. One wire is basically stating, hey, I'm going to compare all of the other electric potentials to this point. So that black wire or the black probe on a voltmeter is kind of like saying this location will be 0 volts of electric potential. And then wherever I put the red probe is going to compare the potential there to the black probe that we're saying is 0 or ground. Okie dokie. So when we talk about electric potential, we can define electric potential as the energy per charge, or how much energy each electron has, or how much oomph or how much an electron wants to jump from one spot to another. It can also sometimes be thought of as electrical pressure. When we think about different analogies, electrical pressure is sometimes used. Okay, so when we talk about electric potential, we're talking about it as per charge. We're not talking about all of the charges, but it's like at a location, it's energy per charge. One electron could have 12 volts of potential, or a bajillion electrons could all have 12 volts of potential. That means 12 volts of potential each charge. All right. So we're going to go through and make these connections and record the potential difference, or the voltage at one spot compared to another, the electric potential at one spot compared to another. We're going to use this simulation to do this. So we're just going to open up the simulation and grab a battery. The black probe or black wire from the voltmeter will attach to the negative side of the battery, the red to the positive, and we'll just compare what's the difference in potential. So clicking over here, floop, there we go. Battery, oops, trying to make it the same orientation as the other thing. Want to get that out of the way so I can click there, bring this over. Okie dokie. So we had the black probe on the negative terminal of the battery there. The little knobby part is usually the positive terminal. We'll go there, floop, 9 volts. So this is saying this will be zero, but that's what the voltmeter does. It says this is zero, wherever this is zero, and we compare the potential here to there, right? If I put them both at the same spot, well, if this is zero, the potential where zero, well, it's zero, right? We're going to compare zero to it's just going to always be zero. If they're at the same spot, it'll be zero. Here, we're saying this location will be zero, and measuring it here, this location is 9 volts. So the difference in potential from here to here is 9 volts. 9 volts, 9 joules of energy per charge. Scrolling down, we just flippity flop the battery. So I'm going to go here, and there's a nice delightful button to flippity flop. And now we're saying if this is zero, this is -9. It's like the other way around. This, let's see, you know what? Here, I'm going to do it this way because maybe flipping it doesn't make as much sense. If I'm saying this side is zero, and then this side is 9 below that, or -9. So that's kind of what we're saying there. If we have it flipped, we're now saying this side is zero, and the difference is still 9, but this location is now 9 below that. So we're at a -9, -9. And now we're going to put the red on the, oh, so now we have it, we just did it that same way, right? So they have us, I think, am I doing this right? Yeah, they have us like this with the red side there, black side there. So we're now saying, remember, no matter what we're saying, this is zero, and then this is 9 below that. So the difference, -9 volts, not amps. Amps is moving charges. This is measuring the energy at those locations. Now we go here. So negative side here, black probe on the negative side. Flippity. So now if we put the black probe over here, we're saying this is zero. Measure that. Hey, +9. This is 9 volts higher than that. 9 volts more than that. Clickety. +9 volts, not amps. Amps measures current or moving charges. This is the energy per charge at a spot. We should put the black wire of the voltmeter on the negative side of the battery, the red wire on the positive side of the battery. What's the potential difference when we connect them like this? Black probe on the negative side like we have now. Red probe on the positive side like we have now. It doesn't, if we do that, the orientation of the battery doesn't matter. Black probe on the negative side, red probe on the positive side, 9 volts, positive 9 volts. Next. So now we're going to be combining batteries. So now we have 2 batteries side by side. Knobby side of one to the flat side of the other, and we'll keep the red on the big positive, black on the negative. Did we have them that way? Or, yep, positive side to the right. So the black probe will go on the negative side of the battery, red probe on the positive. Now we know this one was 9 volts. If we check just this one is 9 volts. So each battery independently is 9. Okay, when we put them side by side, look at that, 18 volts. And that's a positive 18 volts. 18 joules of energy per charge there. We're going to make them three batteries, three batteries. There was 27. Yeah, it's been a long morning, right? Lordy. So now we have 27. 9 times 3, 27. And we have that arranged so that this side is positive, that side is negative, 0. We keep on increasing the amount of energy per charge, 27. Now we go here with 4. So if each battery is 9, if each battery is 9 and now we have 4, that makes 36. There we are. Clickety, 36 volts, 36 joules of energy per charge. There we go. So as we line them up like this, these potential differences, each battery provides 9 joules of energy per charge. This one gives 9 joules of energy per charge that's in the circuit ready to move. Another 9, another 9, another 9. There you go. Next. How much time did we spend on this? Well, if we include the amount of time that I tried to get my computer working, this would be about 15 years. 15 years is not on here, so I think instead we'll have to go with just the amount of time that we spent on the actual questions themselves. And I think that was probably closer to maybe like between 15 minutes, 30. I'll maybe go 30. Click submit. Poof, and then we're done.